Right, so I'm going to go ahead and do number 8 and add to that numbers 12 and 13 to that mix on this particular video. So they kind of seem to me to kind of go hand in hand. So number 8, quick modeling stuff. The amount that we have, we always want to start with our initial condition, and we had 150 of those according to this. Now, a very, very important thing is this idea of compounded. Anytime you have that, that triggers a little bit extra something. So we have 150 initially. We're compounding at 12%, which is 0.12, but it's doing it 12 times per year. And so that's a special thing, and it doesn't show up in any other of these problems, but as soon as you see that phrase compounded, that's an important one to notice. And it does, by the way, say decreasing. I missed that, kind of trying to go quickly through this. So that's losing that. So that means we would start with 100%. And if we type this in, this all comes out to 0.99 to the 12t power. Now, for part B, we again have this, this same idea that we have an exponential story, but we have 540, but it has its own significant word, and that is the word continuous. And as soon as you see that, you know we're talking E, and that would be 0.215t. You'll notice that there's no 1 in this one, because when you have continuous, the E actually has that 100% buried inside it. And notice that this is a positive 0.0215 because it said increasing. If it was decreasing, I'd simply make that a negative 0.215. Now, for part C, it says we have the idea of 275. Again, it says that special idea of compounding. So we are again going to have that rate of 160%. So don't forget, we're moving that decimal over 2 places to express it as a decimal as opposed to a percent, just like I did on this problem. But it's happening 4 times per year, compounding. And of course, this is actually a good answer, but honestly, 1.6 divided by 4 is 0.4. So we could write it as simply 1.4 to the 4t power. And again, trying to go a little bit too fast, don't forget we'd have our 275 out in front. Now again, brought back this idea of continuously again. So we would have 0.045 e to the negative 0.025t. Again, each one of these things compounded monthly. This is it. This one is t in years. This one is years. This one is years. You're supposed to actually say what you're doing the stuff in. This would be t in years. And then our last one is a little bit tricky. It has this idea that sounds almost like compounding, but we don't say it. And so we have 25,000, but we're increasing at that rate of 37%. So I've got 1 plus 0.37, but it's saying that it doesn't happen every year. It says it actually takes 5 years for this to occur. So it's kind of slowing time down to make that happen. And so that's the end of problem number 8. Now, when we go to jumping all the way to problem 12, we're going to jump a little bit. And what we're going to look at is if we actually put some money in the bank. And this would be a very generous bank. We don't get those kind of percentage rates much anymore. But if you started with your investment of $1,500, you put it in at 0.06%, at 6%, again, compounded monthly, so that's 12 times a year, to the 12t power. And it's asking you, like, when would you get an extra 50% on your investment? So what you want to do is we're going to take 1,500 and we're going to multiply that by 0.5. So I want an extra $750 to my investment. Now, but keep in mind, I still had my 1,500 that I had plus my 750. And so we're looking at $2,250. And I want to know, when will I have that? And again, 1 plus 0.06 divided by 12 is 1.005. So what we're going to do is we're going to not only just write that equation out, we're going to actually try to find out what that value, how long should I invest that to get that kind of money? So I'm going to divide both sides by 1,500, and not surprisingly, I get 1.5 because that's 100% plus 50%. I'm going to take the log of both sides, and we can use any base that we want, but my personal preference is I like the natural log. And so what we really have is a fairly simple little idea that we have some numbers. So I'm going to go ahead and take the natural log of 1.5 because that's sitting on the left, and I'm going to divide that by a 12 that is sitting right here and divide that by the natural log of 1.005. And when I did that, I got 6.775. So t equals 6.775 years. It would take almost 7 years for my money to increase by 50% if I put it in at 6%. And then our final question is that we have this new material that we know went from 50 micrograms down to 40 micrograms over a span of 4 years. So we're going to start again with this idea that we have a sub t equals a sub 0 e to the k. Actually, I'm going to do this right this way. I'm going to write it to the t over k, and it should be its half-life, so I'm going to put a half right here. I actually prefer to use the base e, but this is a half-life problem. So this is kind of our overarching thing where k is our half-life. So we're going to try to figure that out. So in this problem, I know that I started with 50, it turned into 40, and that happened over a span of 6 years. So anyway, that's kind of what we have, and I don't know what k is. K is going to be my half-life, the amount of time it took that to happen. And we saw something like that before in this previous problem. Sorry about like moving things around, but notice that what we found, this 37% increase happened in exactly 5 years. So notice I divided by 5 to make that 37% happen. This is a problem where we want it to be losing 50% in that exact same amount of time. So back to our story, what we're going to do is divide both sides by 50, and I'm going to get 0.8. Just like our previous question, we're going to take a log of both sides. That allows me to bring the values down in front. And then a quick cross multiplication would make k natural logs of 0.8 is equal to 6 natural logs of 1/2. And keep in mind that I really want to figure out what k is because that is my half-life. And so all I need to do now is on my calculator, I'm going to take 6 natural logs of 1/2. And I'm going to go ahead and divide that by the natural log of 0.8, and that should provide me with my half-life. And so my half-life, k, is about 18.638 years. It takes 18.638 years for this to be in half. And so one thing it wants to know is what the half-life is, but it also wants to know the equation that models our data. And so my final answer would then be that the amount that I have as a function of time is my initial condition 50 times 1/2 raised to the t over 18.638. And again, it's important when you're dealing with time because time can be measured in so many ways to say t in years. So you'll notice if you used 18.6 for t, that would give you exactly half of it because you'd have an exponent of 1. But at 36 years, you'd have 2 of these half-lives, so you'd only have a quarter left. And that kind of finishes up that chunk. And so hopefully that's helpful, and I'll see you back in class.